Good. All right, so thank you everyone for dialing in at a slightly different time than usual, since we didn't want to make it later than it already is for Dr. Chauhan. So our presenter today is Dr. Prakash Chauhan. He is the director of the Indian Remote Sensing Institute, and he is also the PI of the imaging infrared spectrometer on the Chandrayaan-2 orbiter, which is still going strong after 2 years. And he will be talking to us today on a recent paper that he and colleagues published titled The Unambiguous Detection of Lunar Water using the Chandrayaan-2 imaging reflectance spectrometer. So without further ado, because I don't want to take up too much of his time, so Dr. Prakash, I will hand it over to you. And I will let you, introduce yourself a little bit more if you would like. And I'll just remind everyone to put themselves on mute unless you are speaking. And videos, feel free to have your videos on or off. It's up to you, whatever you're comfortable with. And so, Dr. Prakash, would you prefer if we interrupt you if we have questions, or would you prefer if we wait until the end? Either is fine.
Maybe I think if some pressing question is there in between, that's fine. Otherwise, I have only 25 slides, so I will finish it maybe in 40 minutes or so, and then we can have a good discussion session, because still we will be left with time.
Mm-hmm. Excellent, sounds good. So, folks, if you have questions, if you worry about forgetting it, go ahead and put it in the chat, but otherwise, hold on to it until the end, and we will save discussion for the end. So with that, Dr. Prakash, over to you.
Thank you very much, Parvati. First of all, I would like to thank the group as well as Dr. Parvati for inviting me to this forum and allowing us to make a presentation on this important findings of our Chandrayaan-2 infrared spectrometers with the global lunar community. And I see the presence of the stalwarts of lunar science today. And I'm so thrilled to see Carly. We have been interacting during Chandrayaan-1 days in a very extensive fashion. She has visited our laboratories, but in between we have lost touch. So it's wonderful to see you, Carly, over here. And then many other colleagues from US and other parts of the world have joined. Thanks a lot and greetings from India. One correction I would like to make that I used to be the principal investigator a few years back till I was at Space Application Center of Indian Space Research Organization. And after, I shifted to Indian Institute of Remote Sensing in 2018. My other colleagues are now looking after the responsibility of the principal investigator, and I am more of continuing my interest in this instrument as a science team lead. Otherwise, just to give a brief about me, I am a exploration geophysicist. I've done my master's in applied geophysics from IIT Roorkee, and then did my master's in physics from Gujarat University in India. And I have almost 3 decades of experience in working in ISRO for the use of various kind of Earth observation and lunar remote sensing datasets. My interest lies in the spectroscopy and high resolution optical imaging of Moon and Mars, as well as, of course, for various Earth observation instrument where I have worked extensively, mainly for ocean color. And nowadays, once I have shifted to Himalayan terrain, I've been pursuing the geology and geoscience of Himalayan glaciers. So I'll not talk much about all those things. So quickly, I will come to the topic today, which we are going to talk about. And the title, as has been told by Parvati, is about the detection, which we call unambiguous detection. We can debate it afterwards, of the lunar water using Chandrayaan-2 imaging reflectance spectroscopy. Yeah. So as many of you are aware, as far as the moon, early thinking and thought process of lunar scientists, we have come a long way in last 1.5 decade, where the thinking about moon from bone dry to hydrated moon has emerged considerably by various kind of satellite-based orbital data analysis, which has changed this perception about the moon, as well as the revised analysis of returned lunar samples by various experiments and by various researchers. So in fact, the early evidences about the presence of hydrogen in the lunar polar regions, basically came from the lunar perspective data. And then we have the cell-cross impacts. Basically, the ejecta of these impacts were analyzed through spectroscopic means. And then people could find definite signatures of water in the ejecta from L-cross experimentation, and both in south and northern polar regions, based on other data sets, which I will talk about later. The primary targets like Shackleton crater, Amston crater, Cabot crater in northern pole, some of these were identified as primary targets where water, either in molecular form or maybe in the form of water ice, could have been there. Of course, all of you are aware that the lunar poles have this very cold regions, which are normally described as the cold traps, and Diviner observations has provided us for the first time the temperature range of these regions, which can be as low as 20 Kelvin, and then of course in certain locations in polar regions it can go as high as 300 K or so. So this extreme temperature variability on the moon, especially in the polar regions, and then some of these polar craters are also called permanently shadowed craters because they never receive the sunlight. They are supposed to be very conducive, locations for the water ice storage. And some of these findings were also, confirmed by experiments from Chandrayaan-1, especially from the mini SAR data, and later on by the other SAR instruments on LRO. And then, of course, we have another now dual frequency SAR working on Chandrayaan-2. And then later on, earlier, detection of hydrogen was also confirmed by the land observations, as well as simultaneously from Chandrayaan-1. There was a probe called Moon Impact Probe, basically, which descended from the Chandrayaan-1 orbiter. And then, while it was descending towards the lunar surface, there was a mass spectrometer. And there is a publication by ISRO colleagues where they found very close to the lunar exosphere the presence of water molecules. Later on, Carly is here today. She was instrumental for this fantastic work using lunar reflectance spectroscopy with Moon Mineralogy Mapper, which was a hyperspectral instrument operating from almost 0.4 nanometers, 0.4 microns to 3 micron spectral region. In 2009, these data sets from 3 different spectrometers, Chandrayaan-1 M3 by Peiters et al. And then we have the deep impact paper also by Sunshine et al. And then, of course, Cassini, which was having, these 2 instruments were having the longer wavelength range up to 5 micron. But of course, these were flyby, observations at a very coarse resolution. So Cassini results were also published by Clark et al. So these 3 papers, they describe the use of reflectance spectroscopy in terms of detecting what we call as the total water, which can be the adsorbed hydroxyl or can also be H2O at 3 micron absorption range. These are the results from Deep Impact Probe and Cassini. Both of them were having spectral range up to 5 microns, and that at 3 micron, you can see, there was a significant amount of absorption caused to the reflected radiation at 3 micron. And Chandrayaan-1 also, which Chandrayaan-1 M3 instrument also saw these absorptions while going from equator to polar regions. But the spectral range of Chandrayaan-1 Moon Mineralogy Mapper instrument was limited to 3 microns. So you could not characterize this full absorption curve. at a higher spatial resolution. However, nonetheless, the first and initial distribution of H2O or OH findings were published in Science, and this is the famous picture from the Science magazine, where the concentration of these absorption features were found to be limited to the both polar regions, North Pole as well as South Pole. Simultaneously, at the same time, the publications were also there where people published results by another means, by analyzing the pyroclastic beads from the return samples from the moon. And then they also found that there is a significant amount of water present in these pyroclastic beads also, where the distributions were varying from the surface to the inner core of these pyroclastic bead material. So to put in a nutshell, we had multiple combinations of observations which were suggesting that there can be hydrogen, there could be OH, there can be H2O, which can be found in various different environments on the moon. Saul et al.'s paper, if you have to put it in one word, they found that in primitive lunar magmas, they found occurrence of water or the other volatiles, water or OH. Then, of course, the MQ findings where the polar surface through solar wind was suggested to have presence of OH or H2O. Then, of course, there were results from the SAR experiments where in the permanently shadowed regions, Spurious et al. And then later other people also found that using the circular polarization ratio from synthetic aperture radar datasets that there could be presence of water ice. And then, of course, using moon impact probes, Sridharan et al. Suggested that in the thin exosphere of moon, very close to the moon surface, there could also be traces of water in the vapor form as well. Later on, the findings of M-Cube data were also extended to the non-polar regions, and a lot of papers came where people started finding absorption lunar spectral reflectance absorption at 3 micron at non-polar locations. Also, there are papers in Nature Geoscience. Some of my colleagues, myself, also published some of the work using M3 data in places like Compton-Wilkovich region, which are very different silicic domes, compositionally very distinct. And on such domes, strong water absorptions were seen and were reported. And people described some of these non-polar absorption features as endogenous, lunar water, which could be trapped while the moon's, the surface itself was evolving. And then, of course, in 2018, we had this paper by Sri et al., where they described the direct detection of lunar ice, water ice in the permanently shadowed areas by doing multiplication of the M-Cube data in terms of resolution and improving the signal to noise ratio. They could find spectral signatures of water ice in various, thinly illuminated or faintly illuminated lunar craters, suggesting for the first time, detecting for the first time the direct evidences of lunar ice. Of course, there were a lot of other papers which were published subsequently on M-Cube data, and I will come to a specific topic of thermal emission subsequently, where a lot of new algorithms were developed. The initial algorithm, which was used to process M-Cube data by Clark et al., was modified based on the lunar surface temperature. And a lot of new findings from the M-Cube data about the presence of water both in space and time has also been published. But coming from these data sets, 3 different reservoirs of lunar water were clearly identified by these findings. And we can summarize that water and other volatiles in lunar magnetic systems, the presence was confirmed. H2O and or OH in a thin layer on the most part of the moon surface using spectroscopic observations were also, found, and direct evidences were reported by various versions of interpretation of M-Cube data. And then, of course, using the synthetic aperture radar and, of course, the hydrogen measurements from various other kind of measurements, especially the gamma ray spectrometers and neutron spectrometers, H2O and other volatiles at lunar poles in icy or in frost form, or maybe because the temperature variations are so different or so large, even at times in vapor forms, probably one can find the signature of water. So we have, you can say that we have water on moon, which can be termed as juvenile water, surface water, and buried water. And the type of, if you look to the time scale or the timeline of these findings, one can summarize that we have the discovery from the lunar internal water by Saul et al., discovery of lunar water, surface water from Cassini, Chandrayaan-1 and Deep Impact, discovery of buried water by, in the PSR by L-Cross experiments, discovery of surface ice, of course, on the other, planets like Mercury, etc. And then, of course, there are multiple interpretations of M3 data based on various different algorithms on thermal, emission corrections, which also suggest variations in the presence of water molecules or water or OH molecules in space and time. Now, coming specifically to the reflectance spectroscopy, which is the topic of today's talk, if you look across the electromagnetic spectrum in terms of the water absorption, mainly at the lunar surface, two spectral regions are very prominent. One is at 3 micron, where the water-related absorption is much stronger, and there are also observations or absorption features present at the 6 micron, which is purely due to the water molecules. At 3 micron, it can be a combination of hydroxyl as well as the water molecule itself. And of course, at around 3.1 micron, you also do have the spectral signature for the water ice. So this band basically has a combination of 3 different forms of water at 3 micron. And of course, recently, many of you also must have come across the findings of SOFIA mission, which is basically an infrared telescope, and which has also taken Earth-based observations of moon and confirmed the 6 micron absorption at various locations on the moon, is also published. However, the 3 micron absorption is pretty stronger, and this also has been extensively used by various researchers in terms of producing the lab-based results. So these are the laboratory spectrums of various Apollo samples at around 3 micron, where you have these double absorptions, maybe by OH or H2O, causing a doublet at the 3 micron region. And then, of course, there are extensive spectral observations for the hydrated minerals, where various bands, let's say at around 1.4 micron, 1.9 micron, and then of course this 3 micron region, which is the most significant absorption band, where both OH and water has, a characteristic absorption, has also been documented pretty significantly. And if you look to the recent simulations, so this is the work from Dyer et al. I quote, they've also simulated the finer spectral variability for OH plus H2O in anorthite rocks, the pure water signatures, as well as OH and H2O in the glasses. So there is a considerable amount of variation in the spectral, peaks or spectral absorption peaks, mainly for OH-dominated surfaces. The absorption may occur at around 2.8 or around 2,856 nanometers, and with the presence of H2O molecules, it shifts towards the longer wavelengths around 2,960 nanometers. And then for the cases of water ice, the absorption can be around 3.1 micron or so. So if you sample, or if you design an experiment where you have higher spectral resolution along with higher spatial resolution, it may be possible to discriminate these 3 different forms, or the nature of water, nature of volatiles, or nature of form of water at the lunar surface. In case of AMCube, as many of you are aware, it has good spatial resolution, but since it was meant mainly for mineralogical mapping, it was having a spectral range which was limited up to 3 micron. So this full curve of spectral absorption at 3 micron could not be characterized. And this was the major limitation of M-cube data, because the data was truncating at 3 micron. And in case of spectrometers, in fact, few last bands will also have very poor signal to noise ratio. So in fact, much before 3 micron, some of the data was, the useful data was limited probably much before up to 3 micron bands. This 3 micron band is also affected by a significant amount of thermal emission. So remember, we are basically talking about reflectance spectroscopy. But as you go towards the longer wavelengths beyond 2 micron, the lunar surface, because moon has significant amount of temperature variability. So based on the Planck's law of thermal emission, from 2 micron onwards, a significant buildup in the thermal emission from the moon also starts taking place. And at 3 micron range, you have a composite signal of both lunar reflectance as well as lunar emission, which has significant bearing in precisely determining the amount of lunar water absorption at 3 microns. So one needs to be very careful, in terms of correcting for these thermal emissions. And to do so, ideally speaking, you should have the concurrent lunar temperature measurements from your data sets, which was a limitation in case of M-cube. The initial models were based on extrapolation of the spectral range data from, let's say, 1.5 microns to 2.5 microns into the thermal region. And subsequent interpretations were also done using the diviner data sets, which were basically, lunar surface temperature, but they were not concurrent. As you may agree that with respect to the solar incidence angle, the local solar temperature can vary significantly at different locations. So these were some of the ambiguities in the measurements, which basically came from moon mineralogy mapper data. There were uncertainty about the nature of hydration, and multiple interpretation of M-cube data based on thermal corrections were showed. Many of them have different results as far as the quantification and the amount of water and the nature of water were concerned. There were also certain questions. In fact, some of them were addressed by M-cube also about the mineralogical and temperature control of water and OH in terms of latitudinal dependencies. So with these limitations, the next generation of spectrometers, when we were discussing our Chandrayaan-2 mission, the discussion started here in India that what type of next generation of spectrometer we should plan for our Chandrayaan-2 mission. And in fact, I would like to spend some more time here talking about the thermal correction issue on the lunar surface reflectance spectra for accurate characterization of 3 micron hydration feature. So as you can see, this is the M-cube, this is the diviner lunar surface temperature map. And there are cycles of cold and very hot conditions on moons because of the sun and the moon geometries. At one location, the sun will be shining for a long duration, and the temperature can be as high as 450 K. And during the lunar nights, the temperature can go down up to less than 50 Kelvin or so. So there is a significant amount of variation in the lunar surface temperature. And if you see the simulations of the lunar radiances with respect to varying temperature regime, of course, this is for one thermal condition at hot temperature. So beyond 3 micron, there is a significant buildup in terms of lunar radiance with emission. And of course, this is the reflected component. So that is what we need to worry about when we are dealing with this 3 micron data. And of course, using the Planck's law of radiation, one can also simulate very easily for varying lunar surface temperature, what will be this thermal radiance contribution. So this is from 290 Kelvin to 370, you will see the temperature built up, changes in an almost exponential manner. So when you are moving from very hot moon to relatively colder regions towards the polar, surfaces, definitely this temperature variability and the thermal emission varies significantly in space and time. So this is the kind of observation which, of course, these are some of the various interpretations of M3 thermal corrections. These were the initial ones from the Clark et al. And later on, Banfield and some other workers, they used the the Diviner thermal temperature data to correct for some of these emissions. And they found that later on that most of this spectral signature or the spectrals were showing significant amount of absorption. And they come out with results that most of the part of the moon has some form of lunar hydration based on these interpretations by various algorithms. So we can say that M-Cube discovered water or OH presence, but it was not optimized for accurate measurements. Ideal to have simultaneous temperature measurements along with the reflectance data. So keeping these things in mind, we had started developing some lunar radiance modeling efforts. And this is the kind of signal which we were expecting from a spectrometer which operates from, let's say, 0.85 micron or 850 nanometers up to 5 micron. The red line shows you the total signal. And then, of course, the blue dashed line shows you the reflected component. And for a temperature of around 328 K, the red line over here shows you the thermal emission component. And if you club both of them, the reflected and the emitted spectrums, you can reconstruct the total signal. So the problem becomes an inverse problem when you have the spectrometer data. You have this total composite signal from reflectance as well as emission, and then you have to remove this emission to effectively generate 3 micron absorption features which are corrected for this thermal effects. So there are other papers. Honeywell is probably, I think, attending this talk. She has published this work with this IAR-TF datasets, where she has very nicely brought out the sensitivity of 3 micron to the accuracy of thermal retrieval or the temperature retrieval. So for a spectra, which is from 297K model, the black line is over here. And if you have temperature measurement uncertainty plus minus 2K, then the thermally corrected spectra looks like in somewhat what you see here in green color. And when you have large uncertainties like plus minus 5K and plus minus 10K, the spectra behaves in a very different manner. So essentially what it tells that we should ideally have, as good as you can have the, or as minimum as you can have the temperature uncertainties in your measurements, preferably less than 5 Kelvin or so, so that you can at least in the 3 micron range, can very effectively assess the 3 micron absorption feature while you start working towards finding the differences between OH, H2O. And of course, in case of ice, since polar regions, most of the polar regions are less than 300 K, at times you may not require this thermal correction at 3 micron for colder surfaces. So now I come to our this Chandrayaan-2 mission. Of course, this was a 3-tier mission, which was supposed to have this orbiter. There was also a landing experiment. There was a lander, which was carried on the orbiter, and lander also carried a rover. But as many of you are aware, the soft landing from Chandrayaan-2 lander could not be successfully accomplished. So currently, we have this orbiter, which is going around the surface of the moon since 2019, and we have almost completed 2 years of observations of the moon surface. And we have these 5 instruments. There is another one instrument which is not listed in this list. I will talk about that also briefly. So we have this Chandrayaan-2 large area soft X-ray spectrometer called CLASS, which is associated with solar X-ray monitor, which is basically measuring the incoming solar flux in X-rays to support the CLASS observations, which is basically coming from the lunar surface. And the purpose of this instrument is to detect the lunar elements. Shyama is over here. She is the PI of the instrument. We have also dual frequency L and S band synthetic aperture radar, basically to come over the ambiguities of the observations of the single frequency S band measurements in the polar regions, especially to unambiguously detect water ice. So a few of my colleagues are working on this data. Probably we are getting very exciting results, and some of you will see those results pretty soon in the press. Then, of course, I will talk about this imaging infrared spectrometer, which basically had a spectral range from 0.8 to 5 microns to investigate lunar minerals, as well as primarily to investigate signatures of water and hydroxyl molecules. Then, of course, we had this terrain mapping camera in Chandrayaan-1, which is a high-resolution camera at 5-meter spatial resolutions, looking the lunar surface from 3 different views, so that using stereoscopy, using this data, we can generate 3-dimensional surf topography or 3D imaging of moon at 5-meter spatial resolution. Data sets can give you a 10-meter digital elevation along with the high-resolution images. And of course, the 5th instrument is Chase instrument. Basically, it's a mass spectrometer working from 1 to 300 AMU range for providing the information about near exospheric molecules around the moon surface. And of course, there is another instrument later on which was added. It's called OHRC, Optical High Resolution Camera Set, which has a spatial resolution of around 20 centimeters or so. And it has been designed to operate in very low light conditions, especially in the polar regions, to do a very high resolution imaging of the lunar polar regions. The basic purpose of that camera was to support our landing experiment. But now some of this data is also being used for mapping the lunar poles at very high spatial resolution, and especially in low light and faintly illuminated dark craters in the lunar poles. So now coming specifically to Chandrayaan imaging IRS spectrometers, the basic purpose was to extend the spectral range with higher spatial resolution to overcome some of these ambiguities and to answer questions related to the form, abundance, and distribution of water and OH across various regions on the moon. Also test whether is there any variation of these signatures with time, either during the lunar day or maybe during the repeat observations. Then also associate some of these lunar absorption features at 3 micron with the geological information which is already available from M3 or also can be derived using this spectrometer. And then also understand about the localized anomalies of the lunar hydration at different locations. So we had, this is the picture of the spectrometer. The details of it are published by Rai Chaudhary et al. In 2020 in Current Science. So it has a spatial resolution of 80 meters, a swath of 20 kilometers. And then, of course, this is a 2-dimensional detector array. The number of spectral channels are 256. The spectral bandwidths are ranging from 0.78, but effective from 0.8 micron onwards up to 5 microns. With 10 nanometer spectral sampling, we have 256 nanometers across the entire spectral range with 14-bit quantization. And there is a light dispersing elements through a grating, which is based on spectral separation, grating-based spectral separation for dispersing the light. And then, of course, we have 2 different gain settings depending on the lunar radiation. Especially, it is very useful for low light conditions in the low lunar polar areas where we can go for higher exposure and for another lunar gain setting, and signal to noise ratio can be improved by changing the exposure rates of the camera systems. And the payload is operating from 100 kilometer altitude. And this is the some of the data set which you see over here is that hyperspectral data cube over some lunar surface region. Now coming specifically to the initial or the first few data sets analysis, which we started getting immediately a few days after the lunar insertion of Chandrayaan-2 orbiter happened. We had this enhanced spectral range and spectral resolution for unambiguous spectral measurements, and especially at 3 micron. We also had an extended spectral range up to 5 micron. Out of that, at least from 4.5 to 5 micron region, can be effectively used to reconstruct the lunar surface temperature. I will show some examples of that. Even though it's not ideal spectral range for lunar surface temperature estimation, but it is a good range, especially for the temperatures which we are interested in. And this temperature estimations, can be used to correct for the thermal emissions. And of course, the mission, as the mission people tells us, is likely to sustain for almost 4 to 6 years. And we expect that large number of repeated observations of multiple places will be available for different incidence angles. So initial data set I show you here, this data strip is over Aristarchus crater, which is basically encompassing from 32° north latitudes and going all the way up to 62° north region. This is the the first spectrum which I show over 3 different latitude regions. This spectra, which is marked here in C, is coming from the lower latitudes, 32° or so. So lunar temperatures at these regions is expected to be higher, and you see a good amount of thermal signal building up from this low latitude region, and then of course intermediate latitude at 54° north, and then of course the 61° north latitude spectra, which basically is much cooler compared to what you have at the 32° north. So basically what you see, not only there is a variability in the reflected signal across as a function of latitudinal dependence, there is a good sensitivity of the detector in terms of detecting the temperatures at different locations. These 3 regions, these bars which you see, these are the locations of order sorting filters. Here, these are the locations where the spectrometers are optically joining each other. So we have some issues with our scientists are working to correct for low, response of the detector in this region. So currently, I am putting these bars because suddenly the signal will drop in this region. But you can see there is a good continuity across this order sorting filters. So basically 3 spectrometers have joined to make this full spectral range up to 5 micron. Then, of course, we have to have a solar spectrum, which is the mean average solar spectrum for this data from 0.8 microns going all the way 5 microns. So using this solar spectrum, and then of course, the typically known equations for converting solar radiance to surface apparent reflectance, which essentially involves dividing the radiance data to the solar flux multiplied by the cosine of the incidence angle, and the distance factor between sun and moon geometry, and of course multiplication by the pi to make it unitless. One can convert these radiance observations into the reflectance observations, and this is how for those 3 spectra the reflectance data looks like. So as you can see, there is a strong lunar thermal emission which is inbuilt into the reflectance spectrum of the data. So what if you zoom up or if you zoom up to 3 micron or so, you can see this variability of spectra in you can see the spectral variability from 0.8 to, let's say, up to 3.45 3,400 micron. And for each of these observations, you can see there is for the hotter pixels, suddenly the spectra rises above 2,500 micron in exponential fashion, and for a relatively cooler pixel, the thermal excess is pretty less. So this clearly tells you that if you zoom it up, this particular spectra, you start seeing, the effects of thermal emission beyond 2,000 micrometers or so in IARS spectrums. So one need to do some little bit of modeling to correct these thermal emissions. And to begin with, the thermal emissions or the lunar surface temperature is also a function of spectral wave. It's a function of wavelength as well as the emissivity for different lunar rocks. Now it's a challenge to make accurate measurements of lunar surface emissivity. So many researchers, even for the analysis of deep impact data, etc., they have started the initial work with assuming a lunar emissivity factor, which can vary from 0.9 to, let's say, 0.99. We have also used a assumption that we assume for the entire strip of, which we are going to process, the lunar emissivity factor of 0.95 or so. And I will show you the sensitivity analysis for this assumption, that how much effect it will make on the lunar surface temperature estimation. So with this kind of modeling, one can go and invert from this spectral region, especially between 4,500 nanometers to 4,800 nanometers, by inverting the Planck's law using the observations which we were getting from our spectrometers. So for wavelengths greater than 4.5 micron, we can assume that the solar component in the received energy is very negligible and only thermal excess emission is received. And then by these assumptions, we can invert the Planck's law, and a assumed value of emissivity of 0.95 was used, and rest of them are basically constant. Wavelengths are also known. So between 4,500 and 4,800 nanometers, I show you this results of inversion for various surfaces. And at these wavelength region, more or less, wavelength independent temperature estimates are retrieved. And if you combine, or if you take a normal arithmetic average between this region, you can assign to a pixel an average surface temperature value for that particular pixel in question, and generate this type of lunar surface temperature maps. So here you can see for the strip which I was talking about, the lunar surface temperature are ranging between 380 to around 100K or so. And in the lunar crater also, you can see there is a good amount of variation. So this is the flank, which is the sunlit flank, which is relatively warmer compared to the lunar surface, lunar crater rim, which is in the shadow. So this is the shadow region, and this is the region where the sun is shining. And then as you go towards the higher latitude, the temperature starts dropping significantly because it is expected to drop. So what is the penalty of these assumptions? So these are some of the uncertainty numbers. So if you assume emissivity value of around 0.95 or so, and zoom little with these data sets, and if you have emissivity of, let's say, 0.85, 0.9, and 0.99, if you make these measurements and combine these analyses, you will find that a assumption of constant emissivity will lead you with temperature uncertainty of around 3 to 5K. So now this 3 to 5K uncertainty, how much change it is producing in the lunar emissions in terms of surface temperature corrections, which is of the order of less than 3% or so. So these are the results of lunar the thermal emission correction. This particular spectra is the original spectra, and the derived temperature for this spectra is around 352K with the emissivity of 0.95. And these small variations, which you see over here, are basically for different emissivity values. So we can conclude that by assuming an emissivity of 0.95 or so, in most of the cases, our thermal correction uncertainty at 3 micron is less than 3% around the mean. And these are some of the spectrums for where you can see in the original data, there is a hump over here at 3 micron. And if you correct for the estimated temperature, the thermal emission becomes, or the absorption at 3 micron becomes much, much stronger what it was in the original data. And these are all these two cases where you don't have really a strong absorption at 3 micron in your the measured spectrum. And then once you correct it for the temperature emission, there is a small absorption which you see at 3 micron. But some of these spectrums, and I will show you from where these spectrums are coming up, you already see a absorption in the original spectra. And when you correct for the thermal effects, the absorption deepens. So these were some of the initial results, and then we mapped these data sets for much wider number of observations. So here we reported in this paper 3 observations to begin with. Now we have a lot of data, almost 80% of the moon has been covered. At the time when this paper was written, we have limited observations, virtually no observations in the polar regions. But now, as the time has progressed, around 85% of the moon has already been covered by these observations. So these are the three observations which are chosen to report in this paper, which was basically to give an idea about the initial analysis of our data set. So there was a fairly good geological diversity. So this strip is passing from Mare and going over to the highland regions, similarly over Mare Frigoris, this particular strip. And the third strip was basically over the far side of the moon, mainly covering the lunar highland regions. And this is the kind of temperature regimes we could invert using the algorithm which I described to you. So of course, as you can see, over Mare regions, you have much higher temperatures, and as you go towards the higher latitudes, around 60° north or so, the temperature starts dropping. And of course, depending on the surface composition also, there are variations in the surface temperature. And of course, these observations are for relatively slightly different incidence angles. So that also plays up in terms of temperature retrieval at different locations. So using these data sets, here we show you 4 different cases of a spectrum. So this is the original spectrum. This is the corrected spectrum for a temperature of around 352 K. This is 325 K absorption spectrum, which gives you an idea of a strong 3 micron absorption over here, which basically broadens when you correct it for the emission effect. And then these are the 3 spectrums which we have reported in our paper. Of course, there are millions of such data sets, because when you do spectroscopy for each pixel, you can reconstruct such kind of spectrums. So this is a typical spectrum on bright anorthostatic surfaces. What we found that the bright anorthostatic surfaces has a very strong and very deep absorption, and the absorption, the peak of the absorption also shifts towards, even certain cases beyond 3 micron also. And then for the darker lunar Mare surfaces at the lower latitudes, virtually there is very small amount of absorption. And then when you have, this is a lunar highland ejecta region where you have a situation which is in between. So you can say that there's almost kind of 3 end members for lunar dark mares at higher latitudes, at the lower latitudes, where the temperature is much higher. The lunar absorptions were missing, but as you were going onto the brighter surfaces, even in the the lower latitudes with higher temperature, we could see that over anorthostatic terrains we had stronger absorption features. And similarly, this is the data from another strip which also shows very strong absorption, different nature of absorptions at different locations. So these initial results were pretty exciting, and we were able to see almost the full spectral range, starting from somewhere around 2,600 nanometers, and then going all the way up to 3.3 micrometers or so. In fact, we had a order sorting issue at around 3.3 microns. So most of the data, or the good quality data, is limited up to 3.3 micron, and of course from 4.5 micron to 5 micron also. But in between, there are certain issues with the drop of the signal because of this, the joining of the 2 spectrometers. This one particular data set I show you in high resolution over Copernicus crater, which is a very important impact crater on the moon, and Carly has done a lot of work on it. The central peak of the Copernicus crater is supposed to be made of, more of mafic minerals like olivine. And then, of course, in nature, there are certain other mixtures also. But this particular, the color image shows you the degree of hydration in terms of the band depth. So this particular curve, this 4 spectral curve, which I show you, the 1 is coming from the central peak. The number 2 is coming from this rim from the brighter region. And curve number 3 and curve number 4 comes from the exterior of this crater, which basically does not show you the absorption at 3 micron, the 3rd and 4th, but see at the location 2 and location 1, there are very strong absorptions. So we could show that these absorptions are varying with respect to the geological settings. as well as, with respect to different locations also. So this is the in spectroscopy, this is the continuum of this curve, and this region below the continuum is known as the band depth. So this is the the integrated band depth at 3 micron, which you see. So at central peak, you can see there is a good signature of lunar hydration, and then as you go towards the exterior of this lunar crater, the lunar hydration drops significantly. So what we are showing you is at 80 meters spatial resolution, how you can map the very small localized feature which are showing you the lunar hydration. This is the power of this spectrometer data, which we are currently operating over the moon surface. Of course, I need to tell you that some of these spectra are smoothened with respect to the noise, which is always there in the spectrometers, and these are basically, by typically spectrally smoothing the data sets and doing certain amount of image processing. We still need to calibrate some of these reflectance spectra with respect to the Apollo lunar landing sites, because few of the landing sites data acquisition is still pending. This is an unpublished work which is likely to get published, but I thought it will be very good to show some results now which are available from the polar region. So this is on the South Pole region around around Scott crater, and this strip is basically going all the way from 70° north and going towards the polar regions, and at different locations over here, which I show you the blow up of this strip at certain segments of this data. At location 1, 2, 3, virtually at all locations, you see very strong absorption features in the polar data, and most of this polar data is at less than 300K temperature. So essentially, we need not worry too much about the emissions in these data sets. And within these band region, you see there is a subtle variability as far as the absorption at around 3 micron is concerned. This is a strip of North Pole, two acquisitions we have put together. So as you move from 60° north towards the polar region, you can see the degree of hydration increases significantly. And the work is in progress on these data sets, and probably much more data in the polar regions, we will be able to publish very soon. So this is just to show you the quantification of the total lunar water. There are standard methods of doing it, which are fairly well documented by Honeywell et al., Millikan, Mustard. I will not go into details of it. Basically, we generate the single scattering albedo and connect it to effective single particle absorption thickness called SPET. And there are empirical relations people have proposed to quantify the water based on the field, the ground-based measurements. So using these type of published algorithms, we implemented and then generated the lunar hydration map. So as you can see over here, we over the Mare regions, and as we go towards the northern latitude regions, and wherever we have in between very bright anorthositic rocks or localized stuff, suddenly you see there is an increase in the hydration strength. And as you go towards more of the northern regions, the hydration strength also increases. But there are a lot of localized patches depending on the the composition, depending upon the localized variation in composition in terms of presence of mare and in terms of presence of highland rocks. A significant amount of variability is seen in some of these lunar hydration measurements or the lunar hydration estimations. Another important question: are the selected lunar rocks or soils or the compositions or latitudes have more enhancements in lunar hydration? So we try to look some of the spectra from that point of view. So these are the spectra coming from the anorthositic terrains at different temperature regimes. So one important thing we notice, as the temperature drops, we could see that some of the spectrums are shifting towards the longer wavelengths and even going all the way at non-polar regions up to even 3.1 microns or so. So we need to really carefully look into these data sets for finer interpretation. Similarly, these are the spectra from the lunar basalts or the mare region. So as in the mare region also from 340K to 305 or 305K. So as the lunar surface becomes more cooler and cooler, the dip or the deep spectral absorption over lunar mares also shifts towards the longer wavelengths. The absorptions are not as deep as you see over the anorthostatic terrains in terms of the strength, but in terms of the spectral variability, the temperature seems to play a very important role. These are some of the another observations which I show you only two curves, which is basically which we interpret as a OH curve, and this we feel that is a bounded H2O curve, which is basically having absorption at around 2,950 nanometers or so, and in this case here it is around 2,850 nanometers or so, and these are the simulations by Hibitis et al. For different scenarios. So using these data sets, which also need much more insight, because now we are getting a lot of data from different places, we need to really critically think that how we can characterize these variations in the lunar spectral absorption and associate it with OH or bound H2O presence. So with these words, I would like to summarize today's talk. What we can conclude is that Chandrayaan-2 IRS data analysis have removed some of those ambiguities which were present in the previous observations, and we are able to detect what we call as the 3-micron total lunar absorption feature. We have simultaneous estimation of lunar surface temperature, which enables us, to a relatively improved thermal correction. We also see enhanced hydration strength over brighter albedo regions with highland lithologies and towards higher latitudes compared to mature mare rocks. We see that in 2.8 to 2.86 micron absorptions are more prominent at mares at warmer temperatures, and 3 to 3.0 micron absorption are present mostly at the higher latitudes for highland rocks. So more analysis of this data is in progress. We are now able to generate more lunar surface temperature maps. And as the mission progresses, we are expecting that we will be able to fill the entire, the moon with this data. And of course, this paper is also produced a lot of, interesting interest across media and then, the journalists and of course the lunar scientific community. So I can say that lunar IRS Chandrayaan-2 science have just started to unravel. It's just started coming out. We have a lot of exciting things in future to come, and probably soon we will be able to release some of this data to international community also. And here also we have big experts of lunar spectroscopy. So probably in future we will always welcome a good collaboration, especially with the international groups. And recently we have organized in ISRO 2 years, we commemorated by organizing a lunar science workshop. And these 3 documents you can find on ISRO website, www.isro.gov.in. Basically, first is the handbook of Chandrayaan-2 payload data and science. Then, of course, this is a handbook on orbiter payloads and data products. And of course, the initial science results from different other payloads are also compiled in this document. So with these words, I would like to thank each one of you for your patience, and also would like to thank Parvati for inviting me to share some of our results with you. Thank you very much.
Awesome. Yeah, thank you so much, Dr. Prakash. I mean, this is very interesting. So we're a little past 1 o'clock, but if it's okay with you, I'd like to continue until 1:10. So maybe for 10 more minutes, just so we have time for a few questions. And I know some people might have to drop off, and that's okay. I will share the recording afterwards. But since it was such an interesting presentation, I do want to leave some time for questions. So questions. So if anyone has questions, and I'm sure people have questions, feel free to either raise your hand or put it in the chat or go ahead and unmute yourself. And I see Carly is appearing, so I will let her go first.
Oh,
Yeah, hi, Carly.
that was a wonderful presentation. Thank you so much. I'm really intrigued about the character of the 3-micron band that you see and how it varies both with temperature, but also lithology. And I'm having a hard time separating that. Is that something that will there be enough data to separate the temperature effects from the lithology, the Mare Highland versus the temperature? Because as you mentioned in your introduction, the OH and the H2O can have a big difference also in terms of what their signature is. So how do we pull it all apart?
Yeah, so you are correct. Actually, it's with these limited data sets, we also had some of these questions in our mind. But now, as we are having more data from different regions of the moon and from different temperature regimes, we hope that probably we will be able to sort out these ambiguities, which are very interesting. But in general, I can tell you that even in the equatorial regions of the moon, as I showed you, in the case of Copernicus crater, where it's not highland rock, central peak is mainly basaltic, we are seeing the absorption features, and then of course, in general, compared to mature mares, wherever you see the fresh rocks or fresh exposures and rough surfaces, we do see high hydration strength. So that is in general we are observing. But as we go towards the higher latitude, of course, temperature plays an important role. So that is another interesting thing. But in the equatorial region, wherever you have the rough surfaces, mainly the fresh material within mares, those regions show you relatively higher absorption compared to the mature regions.
Oh, that's interesting. Very interesting.
Yeah. Yeah. So we need to work out. There are people here, those who do simulations on the interaction of solar wind with this type of surfaces, where you have fractures and other things, where that's a different field altogether. So we need to understand what type of interactions and how these rough regions are playing a role in accumulating more amount of hydration compared to the smooth mare surfaces or mature mare surfaces.
One thing, and I see Casey's online too, you mentioned maturity might also be an issue. And with maturity, you have the accumulation of glasses that can capture some of the hydration within the glass. So what part is captured? What part is this transient temperature variation? There's all these variables that your data may be able to provide new insight into.
Sure, I think that's what we need to look into now more critically, that how this data we can interpret with respect to lithology, the optical maturity, and the surface temperature controls.
Yeah.
Casey.
Hi, yeah, this was a really great talk and the data looks amazing. I'm so happy to see that it's turning out so well. One thing that I was really interested in is the band depth of your 3-micron band and the position that it's at. It's really cool that you're seeing that it changes. And I'm curious to know, do you see it change as a function of temperature, a function of maturity of the soil, a function of lithology? Because there's a McLean et al. 2021 paper that shows that irradiating a Apollo sample can shift the 3-micron band to longer wavelengths when only hydroxyl is present, and that it's not necessarily due to molecular water. So I'm curious to see if you have enough data right now to look into the temperature effect and the irradiation.
Yeah, you are correct. In fact, there are papers, and I have been in touch with Hibitis, who is also involved in simulations of these things. And we had long discussions. So it can happen that for certain surfaces, especially, the anorthostatic rough surfaces, the OH also can shift towards the longer wavelengths. So some of these things are new things which we need to understand while analyzing this data and while also doing a lot of modeling activity in terms of radiative transfer simulations.
Yeah, great. I'm looking forward to seeing more data come out of this. It's great data.
Thank you.
Okay, we have time for one more question. Okay, I'm going to ask one. Carly and Casey asked some of the things I was wondering. I mean, I'm especially interested to see the temporal variations, and if things change with magnetohill passage and so on. But my question is, have you looked at how the temperature and the inferred H2O OH abundance compare with so how does the temperature compare with diviner measured temperatures, and how does the H2O abundance compare with Chandrayaan-1 M-cube measurements, because I think the increase in resolution is really interesting.
So I think we are now doing some of this comparison with M-cube data. Of course, we have the data which is basically coming from the Clark's observations, where the thermal correction later on, a lot of modifications is also happened. So we do see wherever, there are absorption reported, at least those surfaces we see, but we also see absorption wherever it was not reported by the M-cube also. So that is one thing, but later on, probably if we get access to the other interpretations, later interpretations of M-cube data, probably it can start showing it up. As far as the temperature measurements, a comparison with diviner is concerned, that is one thing we have to do it. But there is another issue here. We have to normalize this to certain, viewing geometries of for which the diviner did, because each acquisition is a different solar incidence angle. So one-to-one comparison may not be possible. So where careful comparison is required to be done with respect to diviner measurements. And of course, diviner wavelengths were also slightly different. There are issues related to emissivity and all those things. So there will be certain variations, but since we are not really interested much from the lunar surface temperature perspective, we are more interested from the correction point of view. So at least to begin with, I can say the relative temperature thermal emission corrections are likely to be much improved compared to where you are not having simultaneous temperature estimations.
Thanks. Yeah, that makes sense. Okay, if anyone has one more very quick question, we might have time. But otherwise, thank you again, Dr. Prakash. I mean, this is very exciting, and I understand that you're still working on analyzing a lot of this, and I'm sure I speak for all of us when I say we're really excited to.
We need a lot of people to analyze this huge amount of data. So I think it will be good to have big collaborations with the different groups across US or some other universities. Soon, probably after clearance from the planetary data PDS reviews, some of these data sets will be released to international community. And then I think there will be opportunity for many of us to join in investigations. Thank you.
Excellent. Yeah, very exciting. Okay, so and I see there are some comments in the chat. Very cool talk. Thank you. Congratulations on a fantastic mission results. Keep it going. From John Keller, our LRO, former project scientist, now deputy project scientist. So thank you again. Thanks everyone for dialing in. Thanks Dr. Prakash for an excellent presentation, and stay in touch, and look forward to seeing how the mission goes.
Thank you.
Congratulations and thank you.
All the best to all of you.
Okay, take care everyone. Bye-bye.